So we have a problem with the symmetry. I told you use it. Not only that, but I taught you how to use it. We spent first 3 weeks of the course learning how to use symmetries when we have matrices. It was a very simple idea. You know, you might have a complicated law of nature. Hamiltonian can have many terms. It can be a complicated thing. But if you can prove that your law of nature, written as Hamiltonian, Lagrangian, cost function, whatever, if you can prove that it commutes with your symmetry, as a rule, the generator of symmetry is much simpler than the whole complicated cost function, Lagrangian function, etc. So what you do is you use the symmetry to diagonalize our matrix. In other words, find eigenvectors and eigenvalues of the symmetry using our usual thing. A symmetry is a matrix acting on a vector space. So that matrix has its characteristic equation. It has eigenvalues and eigenvectors. And once we have that in place, then any other function becomes very simple. No matter what dimensionality of the problem is, any other function on the space just becomes an ordinary scalar number on each subspace separately. So that's how you use symmetries. To remind you, let me just rerun how we did it for symmetric, anti-symmetric situation. In this case, we'll call it a two-point lattice. So you have a lattice, it's a circle, but it has only two sides. There is a field at side 0, and there is a field at side 1. A shift operator is very simple on this lattice. Remember, shift operator has zeros on diagonal and 1 above the diagonal, and by periodicity 1 in lower left corner. And that means that if I apply this matrix, what it does is just transposes two elements. So if I apply it twice, I come back. But that means I know what its eigenvalues are because I can write this as sigma minus 1 multiplying sigma plus 1, that'll give me sigma squared minus 1. One eigenvalue is 1. Let me call omega 0 is 1. And the other eigenvalue is minus 1. Eigenvalues, and we have this matrix. We can construct projection operator on the space. It's just 2 by 2 matrix in this case. So projection operator 0 is obtained by taking downstairs the difference of the two eigenvalues, but as they have the opposite signs, they'll add up to 2. Normalization just 1/2. And then if I look at the 0 eigenvalue, this one that's 1, then the other one has minus sign. So I'll find a plus sign there and matrix sigma. And if I write it down, it's, 1, 1, 1, 1. A very simple matrix. The other one, which we tend to call anti-symmetric subspace, we have 1, and then because I'm using the other eigenvalue, I'll just say minus that eigenvalue times 1. And if I write that one out, I get 1, 1, minus 1, minus 1 from the off-diagonal guy. And obviously, if I add them up, I get the identity because off-diagonal guys cancel. And if I try to multiply them, I'll get 0 because, multiplying 1, 1 times 1 minus 1 gets 0 every place. And so now we use our trick. If I look at my lattice state, I can multiply it by 1 but 1 is the sum of these two projection operators. And, in this particular case, if you work a little bit, you can rewrite this as a 1 over square root of 2. This is a vector, so this will be a vector, corresponding to these columns of this guy. This is the symmetric combination. So it says take phi 0, add phi 1 to it, and then we distribute the square roots of 2 between here and there in such a way that this vector has unit length, and then there's the other eigenvector, where I take a difference of the two guys. And this also has a unit length. And this vector points in a 1, 1 direction, and this one points in the 1, minus 1 direction. So they're orthogonal and they're kind of diagonal eigenvectors. So we will write this combination here as phi tilde 0 times the eigenvector in that direction normalized, plus this combination we'll call phi 1, 0 times phi 1. And as you will see, these are things that you know from other cases, but maybe not in discrete setting. This one and this one's are Fourier coefficients of the original state. And these eigenvectors are the Fourier basis, as I will show in all generality very soon.